For my culminating project, I will be doing it on Module 3, which is Graham's Law and the purification of gases, and then van der Waals equation and non-ideal behavior of gases. First, we will be talking about Graham's Law and the purification of gases. It originated in 1929 by Thomas Graham as he made the idea. It states that the rate of diffusion of different gases at one set temperature is inversely proportional to the square root of its density. You might be wondering what the difference between diffusion and diffusion is. The difference is that diffusion means that gas particles spread out, whereas diffusion means that gas particles escape through a small hole. Graham's law works with both, but we will be emphasizing diffusion during this culminating project. For the introduction, we will look at how his equations compare two gases, the rate of how gas A versus how gas B moves. It's based on that all gases at the same temperature have the same average kinetic energy. Therefore, the rate a molecule diffuses or effuses is related directly to the speed it moves. The equation is rate A over rate B equals the square root of the molar mass of gas B over the molar mass of gas A. Now we're going to look at van der Waals equation and the non-ideal behavior of gases and their background. It's named after someone with van der Waals as their last name and was developed in 1873. Van der Waals forces are relatively weak electric forces in gases that attract neutral molecules to one another. There's three types of forces. Dispersion is weak, dipole-dipole, which is medium strength, and hydrogen, which are strong. Now we'll be learning about non-ideal behavior. Normally, we can assume that we can ignore the volume taken up by the imaginary ideal gas molecules, and that gas molecules do not attract or repel each other. Well, this is not always the case. So, we use van der Waals equation. The equation is bracket P plus A times N squared over V squared bracket V minus N times B bracket equals N times R times T, where P equals pressure, A is specific constant for the gas, B is specific constant for that gas, V is volume, R is constant, T is temperature in Kelvin, and N is the amount of moles of gas. Graham's law and purification of gases. Well, effusion lets molecules escape through a tiny hole. Diffusion and effusion have the same ratio of rates. When a gas mixture is put in something with porous walls, the gas will effuse through the tiny openings in the porous wall, but the lighter the gas, the quicker it will go out. We can think of effusion in nuclear energy, such as uranium enrichment. Uranium hexafluoride pumps through vessels that have porous barriers. The gas is then enriched and goes through another diffuser or infuser. After time, the uranium will be enriched enough to make nuclear weapons. Some militaries, such as the US military, actually restrict countries from having uranium hexafluoride so that they are unable to make nuclear weapons to go against them. Now we'll be going a little more into depth about Graham's law. Some of the facts about Graham's law is that we smell because of it. It determines what we smell faster. This is how come we can smell pizza before we can smell a candle that are lit or open at the exact same time. It spreads faster. We can also separate the isotopes of each element using Graham's law. Also, for fusion to happen, the opening of the hole needs to be smaller than the molecule's mean free path. The mean free path is the average distance gas particle travels between collisions with the other gas particles. In van der Waals equation and the non-ideal gas behaviors, A constant is a measure of the magnitude of the attractive forces among the molecules of the gas. The bigger the A value is, the larger the intermolecular forces are. The B constant is a measure of the effective size of the gas molecules. The value of it is 4 times the volume of the gas molecules. This is because the orientation of some molecules when they collide restricts the molecules from entering some spaces. It is more all about the excluded space. We can look at a few things to see how ideal the gas behavior actually is. Through pressure, volume, temperature, amount, compressibility, high pressure, and low temperature and intermolecular forces. For pressure, we can see the force that is put on the gas molecules as they strike a surface. For volume, it's the amount of space that gas molecules take up. For temperature is how fast molecules move, and for the amount is the amount of gas molecules in moles. Then we also look at the other three factors. Compressibility, we can compare the molar volume of real gas versus ideal gas at the same temperature. Then we take the N constant, which is moles, of real gas and measure the volume. Then we do the exact same thing for the ideal gas. We take the ratio of the two, and the closer to 1 as possible of the ratio is ideal. The further away, the less ideal the gas behavior is. For high pressure, we look at real gas. It takes up more volume than ideal gas would due to the additional volume of gas molecules. The more compressed the gas is, the worse error there will be. For low temperature intermolecular forces, this is kind of cool. Intermolecular forces have more effect at low temperatures because molecules have less kinetic energy. Now, we're just going to go over a couple sample problems from the topics that we just went over. The first thing we'll do is using Graham's law. The question is, how much quicker does O2, or oxygen, go through a porous container than SO2? Well, we have to get the molecular weight of oxygen and SO2. O2 is 32.0 grams per mole, and SO2 is 64.0 grams per mole. Then we use the equation, the square root of the molecular weight of SO2 over the square root of the same thing of O2, minus the volume of O2 over the volume of SO2. Continuing to the red part that you will see on the slideshow is the next stage of our equation. The volume of O2 over the volume of SO2 equals the square root of 64 grams per mole over the square root of 32 grams per mole. Now we're on the next slide and we'll be looking at the yellow-orange color. The volume of O2 over the volume of SO2 equals 8 over 5.66. Then the volume of O2 equals 1.41, the ratio of VSO2. Therefore, we can say that O2 diffuses 1.41 times as quick as SO2 does. Now we'll be doing van der Waals equation and the question that we have chosen for that. We will calculate the temperature of 20.0 mole of helium in a 10.0 liter cylinder at 120 atmosphere pressure. A equals 0.0341 liters squared at mole to the negative 2. B equals 0.0237 liters mole to the negative 1. And we'll use the equation bracket P plus AN squared divided by V squared bracket times V minus NB bracket equals nRT, where P equals 120 atm, N equals 20.0 mole, V equals 10.0 liters, and then we're going to put all of those into the equation above that we just stated. So it will become 120 plus 0.0341 times bracket 20.0 divided by 10.0 bracket 2 bracket 10.0 minus 20.0 times 0.0237 bracket equals 20.0 times 0.0821 times T. And R equals 0.0821 because P is in ATM and V is in liters. Then when we simplify that, it becomes bracket 120 plus 0.1364 bracket 10.0 minus 0.5 equals 1.64 times T. And at the very end, T becomes 696. And there we have it. We have used the van der Waals equation in a question. And that's the end of my culminating project, at least for this part of my PowerPoint. I hope you enjoyed and I hope you learned something new, as I sure did.